Engineers at MIT have been working on a new concrete that stores energy, and recent headlines mention a 10-fold increase in the amount of energy it can store. This is a big claim that left me wanting to know more, so I've been doing some digging. By giving concrete the dual purpose of energy storage and structural support, there could be considerable material and cost savings as the world becomes increasingly electrified. But as always, things are more complicated than the headline may have you believe. So I wanted to know, how does this work, and are we going to be living in houses that are also batteries? I respect your time, so let's get straight into this investigation. I'm Ryan Innes, and this is a Zeroth Deep Dive. Now, technically, this is not a battery. I'll let the media off for calling it that though, because I think they just mean energy storage, because it is in fact a supercapacitor. The project at MIT falls under the EC³ lab, which stands for electron-conducting carbon cement, with cement being a crucial ingredient for concrete. Just like a standard supercapacitor, the EC³ stores energy electrostatically rather than electrochemically like lithium-ion batteries or lead-acid batteries that many of us are used to. Now, from the last few videos that I've done for the channel, I actually have been learning a little bit more about supercapacitors and a key difference between standard capacitors and supercapacitors. Whilst standard capacitors store energy using electrons on a flat plate, supercapacitors use an electrolyte and a larger surface area to store ions electrostatically, which creates something called an electric double layer. To get this large surface area, supercapacitors need to find a way to increase the contact area between a liquid electrolyte and the electrode, as this is where the electrostatic charge is stored. Conventional supercapacitors use something like activated carbon to create a highly porous sponge-like structure, which looks really cool under a microscope. This sponge is then flooded with an electrolyte, creating a massive surface area where ions can be electrostatically held, which is how they pack so much more energy into the small place compared to a standard capacitor. Now, this is still like an order of magnitude less energy per kilogram than a lithium-ion battery, but it's a massive step up from a standard capacitor. So from this initial information, I was starting to understand the challenges that the MIT researchers might have been having, because they essentially need all of that electrolyte and carbon nano network to be interacting with each other, as well as having a solid concrete phase weaved within it to make the concrete block. After poking around for a while to try and get access to their scientific paper, I finally caved in and spent 20 of my finest beer tokens to buy it directly from the journal. And as it turns out, they were able to solve that exact problem that I was thinking of, and they could prove it using something called focused ion beam scanning electron microscopy. Now that is a difficult phrase to say. With this method, they were able to create 3D scans of the structures inside their cement paste, and these pictures show the results. You can see 3 different networks. One is for the pores where the liquid electrolyte goes. One is for the carbon that makes up the nanostructure that is the electrodes, and the last one is for the solid cement. With all of these fit together, you end up with the electrolyte, the carbon electrode, and the solid cement that causes the structural stability. This looks promising, but I wanted to see how they did it, and it appears that the key is adding nanocarbon black powder into the cement during the mixing process. By adding enough of this in, the carbon network can be dispersed throughout the cement. This would explain how they have the cement with the carbon throughout it. However, it left me with the question of how do we get the pores in there, which need to be there for the electrolyte to flow within. But then I found this article from Randon Seal, and it cleared things up for me. It is titled, "Concrete is more porous than you think," and it explains that concrete is surprisingly porous, with up to 18% of its volume made up of microscopic pores. It explains that when concrete is poured, it contains excess water that must evaporate during curing, and as that water escapes, it leaves behind a complex network of capillary pores. Well, isn't that bloody convenient? What the researchers were left with is a network of carbon and cement with microscopic pores within it that could be filled with the electrolyte solution, enabling energy storage. What's more is that the carbon in the cement is also attracted to the pores, which means when it's filled with electrolyte, the carbon and electrolyte are next to each other, and that's essential for allowing the electrostatic energy storage. Also, from what I read, there seems to be two ways that you can get the electrolyte solution into those pores. The first way was to dry out the cement using heat, and then have a vacuum to force the electrolyte solution into the pores. But as you can imagine, this doesn't sound very scalable, and I can't imagine it working for buildings of any scale. This is where the second method comes in. Instead of using water in the carbon and cement mixture, they instead use a water-based electrolyte. This means the electrolyte is already within the mixture, and once the cement sufficiently hardens, they were left with a building material with a structural network of cement and a carbon network with the liquid electrolyte already inside of it. The researchers also mentioned that sand and aggregate can be added in to turn the cement into concrete, which is what's needed for buildings. This does slightly reduce the energy storage ability, but not drastically. My first thought here was that if you had a concrete block full of water or water-based electrolyte, is that going to be bad for the performance of it as a building material? However, from what I can tell, there are many stages of concrete formation, and it's common for water to stay in the pores for a considerable amount of time, sometimes forever in the case of dams that are holding back water. There's a joke in engineering that civil engineers just study concrete, and I can see why, because it's an incredibly complicated topic. But from what I can tell, the electrolyte doesn't seem to be a huge concern, though definitely has to be considered, as it might affect the longevity and the corrosiveness of the material, which means some ways of reinforcing the concrete would become impractical. The second thought I had was, how do you keep all of that electrolyte in it and make sure it doesn't dry out? In this paper and the experiments within it, the blocks were put inside an acrylic casing, which looks comically impractical for real buildings. However, I was able to dig up a thesis from someone in the research group who proposed covering the blocks in a sealant like bitumen, which would also encase the current collectors and separators, which turn these concrete electrodes into an actual supercapacitor. After reading all of this, I feel like I got the main idea of how the concrete actually works as a supercapacitor, but it left me wondering, how does this lead to a tenfold increase in energy storage ability? And as it turns out, it almost seems to be a side part of the paper that getting the tenfold increase in energy density is actually a result of switching out that water-based liquid electrolyte that we've just looked at with an organic electrolyte. The organic electrolyte is more expensive and harder to work with, but it boosts the voltage of the supercapacitor from around 1.25 volts to up to 3 volts. This takes the system from an energy density of around 300 watt-hours per meter cubed to around 2000 watt-hours per meter cubed, with the tenfold increase referring to the jump from the worst to the best performing combinations. This tenfold increase in energy storage is then mostly explained by the voltage increase, because the energy storage capabilities of a capacitor is proportional to the voltage squared, meaning that if you increase the voltage by 3 times, you get a 9 times increase in energy storage ability. My conclusion from this is that the 10 times energy storage claim isn't the main story. In fact, I think the main point is how the researchers have managed to make this more practical for real-world applications. They've done this by integrating the nanocarbon into the cement mixture and the electrolyte into the water, which isn't possible for the organic high energy density electrolyte, as that wouldn't activate and hydrate the cement properly. However, this doesn't mean that the water-based electrolyte is at all practical just yet. The late Robert Murray Smith put it perfectly in a video he did a few years back on an original version of this technology.
But that amount of energy is, well, peanuts really.
He was right, and the energy storage density of the water-based electrolyte concrete hasn't come on very far from then. At 300 watt-hours per meter cubed, you would need 45 meters cubed of concrete to replace a Tesla Powerwall, which contains around 13.5 kilowatt hours of storage. From what I can tell, this seems to be roughly the total amount of concrete needed for a standard home, which would mean that all of the foundations would be energy storage. Of course, the more energy-dense electrolyte might only require 5 meters cubed of supercapacitor concrete, which is more like a wall, but that's less practical for other reasons, like how to get the electrolyte into the blocks in the first place. I have been wondering though that I'm not sure this is even a fair comparison, because supercapacitors have never exactly been known for their energy storage capabilities. They're really designed to store large amounts of power and release it very quickly, which is why I've been thinking of some more industrial applications that this might be useful for. Besides, I can imagine plenty of things going wrong if everyone's houses were built on giant concrete supercapacitors, or if you had a wall that was a supercapacitor and you went to try and bang in a nice family photo. The MIT lab has partnered with Aizawa Concrete Corporation, a Japanese industrial leader in high-performance concrete, and I assume they see some potential in the idea. I could personally imagine it being used near energy generation sites to stabilize the output power. For example, maybe in decades to come, the foundations of a wind turbine could use the supercapacitor concrete, helping to smooth the output power. This is a long way off though, and all really depends on the cost. Although the nanocarbon and water-based electrolyte are pretty cheap on their own, the whole cost could quickly explode with additional labour costs and large metal current collectors. The demonstrations are still cool though. During testing, the concrete was used to hold up some weights and light an LED, showing it does technically work, though more research is needed into how mechanical loads affect the electrical performance. Nonetheless, I feel like these experiments are worth doing, and there's definitely some transferable things that will be learned. If you've enjoyed this video, please consider subscribing. It's free and helps the channel a lot. You might also like some of my other videos, like this one on an extremely efficient electric motor. And as always, thanks for watching.